By the early 1940s, the world was consumed by fire, and the skies had become the primary arena of technological contest. The Second World War was, at its heart, an engineering conflict, and engines, not airframes, were the real, decisive weapons. Every nation sought faster fighters, higher altitudes, and longer ranges, knowing that a difference of merely 10 miles per hour could mean the difference between life and death for a pilot, and the survival of a nation. The skies above Britain and Europe were ruled by the magnificent reciprocating engine. The thundering power of the American Pratt & Whitney double Wasp, the brute force of the German Daimler-Benz DB601, and, above all, the superlative elegance of the British Rolls-Royce Merlin. The Merlin, in particular, was an engine of near-mythic status. It powered the Spitfire, the Hurricane, and the Mosquito. It was the acoustic and mechanical signature of the Battle of Britain. Engineers lovingly crafted its complex array of pistons, valves, and superchargers, squeezing every last ounce of performance from high-octane fuel, pushing it ever closer to its physical limits. But those limits were rapidly approaching. The fundamental problem of the reciprocating engine lay not within its internal combustion chambers, but in its external manifestation, the propeller. For decades, the propeller had been the sole mechanism of forward flight. Yet, as designers pushed aircraft speeds past 400 miles per hour, the propeller blades themselves began to encounter their own invisible wall, the speed wall. The tip of a propeller blade, moving in a circle, travels much faster than the aircraft itself. At high speeds, these tips began to approach and even exceed the speed of sound. This resulted in the catastrophic formation of shock waves, a phenomenon known as compressibility. The air over the propeller would be violently disrupted, causing a terrifying loss of efficiency, a violent shuddering of the airframe, and a near-instantaneous drop in thrust. To fly faster than this barrier required disproportionate increases in engine power, which in turn meant massive increases in engine weight, fuel consumption, and cooling requirements, a self-defeating spiral. The engineers were trapped in a technological cul-de-sac. They had perfected the piston engine. To go faster, they needed to abandon it entirely. In the shadows of this frantic arms race, where the roaring Merlin was the king, a small, isolated group of British engineers was building an engine so advanced, so radically simple, that many in the established aviation hierarchy simply refused to believe it could work. It wasn't the loudest or the biggest, but it promised to bypass the speed wall entirely, quietly rewriting the rules of aerial warfare forever. Part 2. The unlikely collaboration and the centrifugal heart. The conceptual genesis of this revolution lay not with the industrial behemoth, Rolls-Royce, but with one solitary man, Frank Whittle. Whittle, a young, relentlessly determined Royal Air Force officer, had first proposed the idea of jet propulsion, the gas turbine, in the late 1920s. He had been ridiculed, dismissed, and starved of funding. The Air Ministry considered his concepts pure fantasy, believing the heat would melt the metal and the fuel consumption would be ruinous. Despite this institutional skepticism, Whittle, scraping together private funding and relying on the sheer force of his technical conviction, finally demonstrated his working prototype, the W.1 unit, in 1937. It was an engineering miracle, a noisy, smoke-belching beast of metal that proved the fundamental principle was sound. Controlled explosions could produce sustained, usable thrust. The outbreak of war in 1939 finally lent Whittle the urgency he needed, but his small company, Power Jets Limited, lacked the industrial scale, the deep pockets, and, crucially, the advanced metallurgical expertise necessary to build a reliable war machine. His prototypes, while functional, were volatile, temperamental, and possessed operational lifespans measured in mere tens of hours. They were delicate laboratory pieces, not engines designed for the brutality of combat. In 1941, the British government, terrified by intelligence reports confirming a parallel, more advanced German jet program, which would eventually yield the Me-262, recognized the desperate need to industrialize Whittle's design. They issued a mandate. The vast, disciplined resources of Rolls-Royce, the undisputed master of the Merlin engine, must take over development. The transfer was not entirely smooth. Whittle, fiercely protective of his life's work, resented the intrusion of the corporate giant. But Rolls-Royce brought something indispensable: industrial elegance and deep engineering genius. Their chief piston engine designer, Sir Harry Ricardo, and the man who would become the driving force of the jet age, Stanley Hooker, approached Whittle's design not with skepticism, but with reverence and a ferocious focus on reliability. Hooker, a brilliant mathematician and fluid dynamicist, instantly saw the latent potential in Whittle's centrifugal flow concept. The centrifugal engine was based on a simple principle. Air is sucked into the center, flung outward by a massive, high-speed impeller like a giant fan, compressed by this sheer centrifugal force, and then ignited and expelled. Rolls-Royce engineers took Whittle's functional but crude W2B design and began the painstaking, complex process of refinement. They saw the volatility in the engine's design, the propensity for compressor stall, the uneven combustion, and set about creating order. The result of this intense collaboration and refinement was the Rolls-Royce Derwent, initially designated as the Welland. The transformation was a masterpiece of wartime engineering. Rolls-Royce didn't fundamentally change Whittle's core centrifugal principle, but they executed it with levels of precision, reliability, and metallurgical artistry that Whittle's small team could only dream of. Metallurgy. The key challenge of the jet engine was heat. The turbine blades and combustion chambers operated at temperatures that would instantly melt conventional steel. Rolls-Royce utilized its decades of experience with high-output piston engines to develop and refine new mnemonic alloys, a family of nickel-chromium superalloys, that could withstand the infernal heat of the turbine section, spinning at over 16,000 revolutions per minute, for hundreds of hours, not tens. Efficiency and simplicity. The Derwent was astoundingly simple compared to the Merlin. It eliminated the complexity of thousands of moving parts. No pistons, no connecting rods, no crankshaft, and no complex valve gear. In place of the rhythmic violence of a reciprocating engine, the Derwent offered a smooth, continuous, rotary motion. It promised twice the power with half the moving parts. Thrust. The first Derwent, the Mk.I., delivered 2,000 pounds of thrust. Its later variants, particularly the Derwent V, would push this to over 3,500 pounds. Power levels that utterly obliterated the thrust-to-weight ratios of any propeller-driven engine of its size. This was the quiet revolution. The Derwent was not just faster, it was fundamentally more reliable and easier to mass-produce than its German counterparts, which were already struggling with the complex demands of the axial flow design. The Derwent was the first jet engine built not as an experiment, but as a practical, production-ready war machine. Part 3. A new kind of thunder and the triumph of reliability. The testing of the Derwent engine took place under a blanket of absolute secrecy, primarily at the Rolls-Royce test facility in Hucknall, Nottinghamshire. The atmosphere was charged with a mix of fear and exultation. The engineers knew they were dealing with the most advanced technology on the planet, a secret that, if compromised, could shift the balance of the war. When the prototypes were wheeled onto the test stands, the sound they made was unlike anything else on the airfield. It was not the familiar, heavy, guttural roar of the Merlin, but a rising, sharp whistle, the sound of air being violently compressed, followed by a fierce, steady howl of expelled gas. Engineers coined the phrase, a new kind of thunder. But it wasn't the sound that mattered, it was the data. The thrust readings shattered all expectations. The engine delivered smooth, continuous thrust across its operational band, and it did so with a degree of mechanical placidity that was shocking to men accustomed to the brutal vibrations of high-power piston engines. Test pilots, initially skeptical, were quickly converted. The reliability was the biggest revelation. When the Derwent was subjected to sustained high-power runs, it simply kept running. Its simpler design meant fewer points of failure. As one test pilot noted, he began to trust the Derwent more than any finely tuned, highly stressed Merlin he had ever flown. The secret was reliability, and this stood in stark, devastating contrast to the German experience. While Germany's engineers were undeniably brilliant, they had focused on the more aerodynamically efficient axial flow design, where air flows straight through the engine. This design promised greater speed potential but was vastly more complex to engineer and required far more sophisticated materials. The German Jumo 004 engine, which powered the dreaded Messerschmitt Me 262, was a fragile beast. Due to the rapid deterioration of its turbine blades under extreme heat, its operational life was often limited to a terrifyingly short 10 to 25 hours. This scarcity of materials and engine lifespan severely hampered German operational readiness, forcing constant replacement and repair. The Rolls-Royce Derwent, by comparison, had an initial design life of 100 hours, and quickly surpassed that. Its robust centrifugal core, while physically wider, creating more drag, was far more forgiving of metallurgical imperfections and far easier to maintain. The Derwent proved the essential wartime equation. An engine running reliably at 90% efficiency is infinitely more valuable than a fragile engine running at 100% efficiency for only 10 hours. The Air Ministry might have initially seen the Derwent as a novelty, but the pilots and maintenance crew saw it for what it was, a rugged, dependable revolution. The Derwent's destiny was inextricably linked to the Gloucester Meteor, the first British jet fighter to be pressed into service. The Meteor was designed specifically to accommodate the Derwent's unique requirements, and the engine's centrifugal bulk necessitated a twin-engine design, with two nacelles hung on the wings. In 1943, the Meteor, fitted with twin Derwents, took to the skies, and the pilots instantly experienced the true meaning of jet power. It wasn't just the flat-out speed, though that was astonishing, but the rate of climb and the ability to maintain power at high altitude where propeller fighters struggled. The Gloucester Meteor, powered by the Derwent, became a symbol of a shift in perception. The piston age was about the mechanical maximum, the jet age was about the effortless, continuous energy provided by the gas turbine. The engine had delivered on its promise, providing Britain with its first true taste of sustained, reliable jet-powered flight. Part 4. Into the Fight, the Geometry of Conflict. The Derwent-powered Meteor did not enter the war in the great dogfights over Europe, but in a peculiar, specialized role that perfectly highlighted the engine's unique advantages, intercepting the V-1 flying bomb. In the summer of 1944, as the D-Day landings secured the beaches of Normandy, Hitler unleashed his final terror weapon, the Vergeltungswaffe 1 V1, or Doodlebug. These pulse jet-powered cruise missiles were faster than many Allied fighters at low altitude, and their unstoppable flight path demanded immediate, high-speed interception before they reached London. The Spitfires and Mustangs struggled. They had to dive to gain the necessary speed, and even then, they could only just keep up, risking structural failure in the process. Then came the Gloucester Meteor, powered by the Derwent V. The Meteor could intercept the V-1s with ease. Its jet propulsion allowed it to accelerate rapidly to the V-1's altitude and speed without the dangerous diving maneuvers required by piston fighters. It didn't dogfight the bomb, it simply outran it. The pilots didn't even need to fire their guns. They would simply fly alongside the V-1, use their wingtip to disrupt the airflow over the bomb's rudder, and send it tumbling harmlessly off course. This simple action, repeated dozens of times, proved the jet's operational superiority in the clearest possible terms. The Derwent delivered the sustained high speed that no propeller engine could match at low level, transforming a desperate race into a methodical, simple procedure. The Meteor and its Derwent engines fundamentally redefined the parameters of air combat. The old rules of the dogfight, the tight, low-speed turn, the stall, the spiral, were rendered obsolete. The piston fighter was defined by its maximum sustained speed and its turning radius, the jet fighter was defined by its energy state. The jet engine allowed the pilot to execute a new geometry of attack. Altitude dominance. The Derwent maintained its efficiency at high altitudes where piston engines choked. This meant the Meteor pilot could choose the terms of engagement, operating far above the enemy and diving down with a speed advantage that was impossible to counter. The boom and zoom. Jet combat became a contest of speed and energy rather than maneuverability. The Meteor's tactic was simple. Use the superior speed of the Derwent to enter the fight, execute a high-speed pass, fire a burst of cannon shells, and then use the engine's power to zoom, climb rapidly, back out of reach before the slower enemy could react. The end of torque. The Derwent delivered thrust cleanly through the jet nozzle, eliminating the powerful torque and gyroscopic effects of the massive propeller. This made the jet a far more stable, precise, and less tiring platform for the pilot, particularly during high-G maneuvers. The Derwent had taken air combat from a spinning dance of propellers into a linear contest of raw speed, climb rate, and sustained energy. The enemy could no longer simply turn and fight, they had to react to a speed advantage they could not match. Part 5. The irony of victory and the global transfer. As the war concluded, Rolls-Royce wasted no time capitalizing on its technical lead. The Derwent had been a phenomenal success, but the engineers knew they could extract far more power from the centrifugal design. Stanley Hooker's team immediately set about designing the engine's successor, a larger, more powerful unit that would become the Rolls-Royce Nene. The Nene, the pinnacle of centrifugal flow technology. It used a double-sided impeller, sucking air from both the front and the rear, vastly increasing the compression ratio and thus the thrust. The Nene delivered over 5,000 pounds of thrust, a figure that put it in a league of its own globally. The Nene was a powerhouse. It flew in the Supermarine Attacker and the Hawker P-1040, the precursor to the Hunter, and became the benchmark for a new generation of British naval and land-based jets. The world had seen its future, and that future was centrifugal. But the immediate end of the war and the beginning of the uneasy peace of the Cold War introduced a complex and fateful geopolitical dimension to the Nene's existence. 12. The fatal commercial decision. After 1945, Britain, exhausted by war and facing immense debts, needed to quickly convert its military technology into exportable commercial goods. The government decided that the future of British aviation lay in the more sophisticated, but still unproven, axial flow designs like the Rolls-Royce Avon. The centrifugal design of the Derwent Nene was therefore deemed expendable for the sake of lucrative exports and foreign sales. Rolls-Royce licensed the Nene design for production in the United States, where it became the Pratt & Whitney J-42, powering the Grumman F-9F Panther, America's first generation of carrier-based jets. This was a logical and profitable commercial move. The truly catastrophic decision, however, came in 1946. At the time, the Soviet Union was struggling desperately to catch up in jet technology. Their own early designs were unreliable, fragile, and dangerously underpowered. Stalin, recognizing the critical nature of the gap, demanded access to Western jet technology. A Soviet delegation, including prominent engineers, arrived in London. They requested licenses to purchase multiple Nene engines. The British government, under the Labour Party, led by Prime Minister Clement Attlee and influenced by the then Minister of Supply, Sir Stafford Cripps, viewed the sale as a gesture of goodwill to a wartime ally and, perhaps, a naive commercial opportunity. Rolls-Royce chairman Lord Hives himself reportedly expressed incredulous concern, warning that the engine was too powerful to sell. Cripps famously brushed aside the warnings, stating that the Soviets, lacking the necessary advanced metallurgy and manufacturing techniques, would take years to reverse engineer the engine. "They'll never be able to copy them," was the sentiment in Whitehall. In an act that would be viewed as catastrophic in hindsight, 40 Rolls-Royce Nene 2 and 15 Derwent V engines were crated up, packaged meticulously, and shipped directly to Moscow. The engines arrived, pristine and complete, a turnkey solution to the Soviets' most pressing technological hurdle. The irony was immediate and cruel. The same brilliant British engine that had protected the skies over Europe, that had vanquished the V-1, was now handed directly to the nation that would become Britain's greatest adversary. The silent work of Hooker and Whittle had become the most decisive geopolitical gift of the early Cold War. Part 6. The Silent Legacy and the Korean Shockwave. The Soviet engineers, led by the Klimov Design Bureau, proved Cripps disastrously wrong. They did not take years, they took months. The Nene, being a simpler, more robust centrifugal design compared to the complex axial flows, was perfectly suited for Soviet manufacturing methods and metallurgy. They meticulously stripped the Nene, catalogued every component, and quickly reverse-engineered it into the Soviet Union's own, slightly scaled-up, production version, the Klimov VK-1. The VK-1 was virtually an exact, metric copy of the Nene. It was reliable, powerful, and, crucially, it was ready for mass production by 1948. The VK-1 was designed to power a radical new Soviet swept-wing airframe, the Mikoyan-Gurevich MiG-15. The MiG-15 was a product of European necessity. Its swept wings were based on captured German research, and its engine was pure Rolls-Royce Nene. The resulting aircraft was a lightweight, high-climbing, powerful fighter that would shock the Western world with its appearance and performance. The global implications of Cripps's gift played out dramatically in the skies over Korea, just 4 years after the Nene engines were shipped to Moscow. In 1950, when the Korean War broke out, American forces expected air superiority, relying on their first-generation jets like the straight-winged F-80 Shooting Star. But when the fighting moved to the border with China, over the infamous area known as MiG Alley, the airspace over the Yalu River, the West faced an astonishing technological shock. The MiG-15 appeared, fast, high-climbing, and devastatingly effective. It immediately outclassed every Allied fighter it faced, forcing the Americans to hastily deploy their best available countermeasure, the swept-wing North American F-86 Sabre. The Great Jet versus Jet duels over the Yalu River were technically battles between an American design, the F-86, and a Soviet design, the MiG-15. But the core of the Soviet advantage lay in the power plant. The MiG-15 was powered by the VK-1, the direct descendant of the Rolls-Royce Nene. The irony was overwhelming and complete. British pilots had been protected by the Derwent from German jets, only to see the next iteration of that same engine, the Nene, now being used by the Soviet Union to challenge the air superiority of their key allies. The engine that had been forgotten in the halls of Whitehall had become the foundation of the Soviet Cold War deterrent. Today, few remember the Derwent or the Nene by name. Modern jet engines are almost universally of the more efficient axial flow design, which can be seen as the ultimate evolution of the German concept. Yet, the legacy of the Derwent Nene remains foundational, proving several principles that hold true for every engine flying today. Reliability wins wars. The Rolls-Royce centrifugal engines proved that a robust, reliable design, even if slightly less aerodynamically efficient than a complex counterpart, is the key to military success and commercial viability. Their sheer durability allowed the British and, later, the Soviets to transition rapidly into the jet age without the crippling maintenance issues that plagued the early German programs. The blueprint for the future. The principles of constant pressure combustion and high-speed rotary compression, pioneered by Whittle and perfected by Rolls-Royce, are the irreducible DNA of every turbine flying today. The Nene provided the technical confidence and the industrial template that proved jet propulsion was not a niche technology, but the inevitable future of all flight. A geopolitical catalyst. The transfer of the Nene acted as a powerful, unintentional catalyst, accelerating the Soviet Union's jet development by perhaps half a decade, directly leading to the fierce technological parity that defined the Cold War. The Derwent and the Nene were quiet, dependable, and unstoppable. They were the engine that first married the theoretical possibility of jet flight with the brute reality of industrial production. They were forgotten pioneers who opened the door to the supersonic age. The world had stepped into the jet age, and it was a forgotten British engine that, for better or worse, provided the global key.